All right. Today, we're going to discuss about naming of welding consumables. And this is somewhat related to terminologies, the way in which we call these things. So much of this is discussed in the Lincoln Procedure Handbook in section 4.1, and also in many AWS standards, which I believe all of those will be available to you through the university library system. And I do recommend you download them. They will be much helpful to you, much money there. The standards are many, right? And what they try to discuss is what the chemistry of the wire, if we have fluxes, what the chemistry of the flux is, and what type of material they're going to provide. So they discuss what the strength of the material is going to be, in some cases, what the toughness of the material is going to be. And this is good for pretty much anything that is welded. We will be focusing on carbon and low alloy steels here, but if you're talking about high alloys, stainless, nickel, aluminum, pretty much everything has a standard. The standards we'll be discussing today, well, very tangentially, because each of these standards is very deep and it's like reading law, right? Are the ones for MIG, metal core, and TIG, for flux core, for subarc welding, and for stick welding. And whether it's carbon steel or low alloy, we have these different standards. But they have some things in common. And the most basic of these things in common is the ones I want to discuss with you. So we can, you can speak the language as based on your knowledge. You can also say what type of electrode should be used, for example. Look, the A5 committee of AWS is the one in charge of having standards for the consumables. And as you see in this list, it is huge and it's ongoing, right? It goes up to 532. I wouldn't be surprised if it has grown. I'm a member of one of these committees that is 513, that is for materials that are made for hard facing, overlays, wear resistant materials. But this is a little one about all of these other things we have, whether it's, look, carbon steel, low aluminum, but even we have magnesium, right? It's so much. Let's start with discussing typical wire and rod sizes. So what I put here is something is not meant for you to choose what wire to use with what plate thickness, although that was original intent. But so you see the range of wires that are typically used. And essentially are these three that are second, third, and fourth. For heavier sections, the fifth and the sixth, right? 0.024, seldom used. 2 millimeter wire, very seldom used, especially when it's solid. But these other diameters, 0.03, 035, 045, 052, and 062, that's 1/16 of an inch, are commonly used. One thing to know, of course, is this is much like bolts and nuts. You could have any diameter you wanted, but once people agreed on a standard, so we have like now one wire of one brand can work with the contact tip and the welding equipment of another brand. So we are in a good situation that promotes exchangeability and is convenient. The other interesting thing is that you get to see we have wire diameters in inches and wire diameters in millimeters that are kind of the same, but not exactly the same because you just can't. And the standard is moving slowly into the millimeter equivalent of the inch standard. Let's talk about the consumables for MIG, metal core, and TIG. In this case, the consumables are under the same standard for naming them. And let's start with this. The name would be something like ER70S2. And I would know immediately that it's a MIG wire. Why? The ER means E for that is an electrode, or R that means a rod. So when I'm doing MIG, I'm pulling the wire, that's my electrode. But when I'm doing TIG, that exact same wire can be cut into lengths of rods. And those are not electrodes because they don't conduct electricity, but those are the ones I feed into the weld pool. So when it's solid material, is ER, electrode or rod, and it's followed by a number. The number can be 70, 80, can be 100. This number is the strength of the weld under. If you do a weld using this consumable under standard conditions, this consumable will have a strength of a strength to failure of 70 KSI. Right? 80 would be 80 KSI, and so on. The higher the number, the stronger the filler metal, but also typically means more hardenable and more difficult to weld, more susceptible to hydrogen. So you know, 70 is a very common number. Pretty much every wire you're gonna see in MIG is 70 of some sort, although there are many others. S indicates it's a solid wire. Now, if we are doing metal core, because it's a metallic sheath, a tube with a powder inside, that is called a composite. And there are other types of wire that are not widely used commercially now. And I said not widely, maybe not at all, in which they would have stranded the wires. We have some samples of that in our lab, right? In which they thread 2 or 3 wires. So all those are called composite wires. Right today, composite means pretty much only one thing, means metal core. So ER70S would be a wire for MIG or a rod for TIG. And E70C would be a wire for metal core. And you see it's E and not ER. And the reason is that if I'm going to cut the metal core wire, when I cut it, the metal powder is going to spill. So you don't use tubular wires as rod. I'm sure there are exceptions, but typically you seldom do. I don't know of any case. And then is followed by a number of things. The one thing I'm going to focus now is the first one, that is a number, that is 2-2-6, and the dash means something in particular. And the meaning of that is listed in the standards. But for example, if I say E70S-2, the standard will tell me I have so much carbon, I have a range of manganese, and a range of silicon. If we say ER70S6, what do you get to see? That the carbon is more or less the same. In this case, I put only one value, and here I put a range that covers this value. But look at the range of manganese is higher. And look at the range of silicon is higher. So although we have discussed these things very loosely, let's say I have a rusty plate. Which one which electrode would you prefer to use? ER70S2 or ER70S6 for welding on a rusty plate? It's MIG welding. I'm paying attention to the chat. Love to hear your thoughts. Oh, interesting. Okay. I have a suggestion for 2 and a suggestion for 6. So let's think together. If the plate is rusty, that means we'll have some amount of oxide, which means oxygen. Oxygen is typically bad for your weld. And how do you take the oxygen out of the weld? You do it by having high silicon or high manganese that are very reactive with oxygen and then float to this surface in the form of silicates or some amount of slag or impurities that float on the weld pool. So yeah, if we wanted to weld a rusty plate, would be ER7ES6. And so here we go. I have in this slide where we talk S2 is when we want to weld when there's no scale or no porosity, or when we're making many passes. Because even if the plate was rusty, after we made the first few passes, we'll be welding over the clean metal of the previous passes. Anybody has a thought of what would happen if I use ER7ES6 over clean plate or after many passes? So let's say I have ER7ES6 and ER7ES2 in welding in very clean plate. Which would be harder? Which would be stronger? Thoughts? I'm waiting to the first guess. Okay, so if I'm welding on clean plate, that means nothing, let's say little to nothing, is reacting with my manganese and my silicon. So my filler wire will be more hardenable because has higher amount of alloying elements. So the S6, that is the one that has more manganese and more silicon, in the absence of oxides, is going to end up being a harder electrode. And I have a question about silicon inclusions. They can happen, but in MIG, typically what happens is they float to the surface and they end up being this, after you weld with MIG, you see sometimes kind of a yellowish, glassy, like spots over the surface of the weld. That is the silicon oxide. That's essentially glass. Those are silicates that come from the silicon that reacted with the oxygen and floated to the top. So now what you would say, okay, I got a stronger wire, I'm happy. Yeah, but you have to be careful because if it is too strong, you might end up having problems of hydrogen cracking, or you might not meet the standards because it became too hard. And there are limits for that. Corrosion resistance is lower in harder materials. So whether you want an S2 and S6, it depends on what your context is and what you need to get. It's not just the stronger the better, or the more the oxidant the better. There are other formulations like G. G is manufacturer dependent. So although G appears in the standard just says whatever the manufacturer wants is a wild card. One possibility, for example, would be to have extra low silicon, and that would be used in places like automotive industry, because with extra low silicon, we would have very few silicate. If we weld on clean plate, we would have very few silicate islands, and then the end weld is clear. All right, that was MIG, metal core, and TIG. Let's switch to stick consumables. And stick consumables have a somewhat similar naming. Okay, I have a question. The question is if the current and voltage will be the same in ER7ES6 and 7ES2 and 7ES6. And the answer is yes. For the case of MIG, we would, if you use the same wires with the same currents, you see pretty much the same, except that the metallurgical result after the weld has been done is going to have different hardness or if it is dirty, you would have gotten better cleanliness. But yeah, current and voltage would be essentially the same. Stick welding. Stick welding, the naming is, starts with E, which is electrode, right? And funny enough, for MIG, we make a difference between electrode, that means comes in a roll, and rod, ER, and rod that is a finite length. In this case, in stick, it is a finite length, but it's an electrode and we call it E. And what is followed is by 2 digits that are the KSI of strength of the weld done under standard conditions. So we would have something like E70 something or E60 something. Those who weld although already know where I'm going. And then the last 2 digits relate to the type of fluxes they have. So if the third digit is a 1, that means this can weld in all position. If it is the third digit is a 2, means it's good for flat and horizontal. And also there is another designation 4 that is quite uncommon. I'll mention that later. And then the last digit, so we would have something, for example, like 61 something, right? That would be 60 KSI, all position. Or 71 something, that means 70 KSI, all position. The last digit is the one that captures the type of slag system we have. So cellulosic would be, cellulosic based on sodium would be a 0, and we would have 6010, which some of you are all too familiar with. If we have a iron filling, lime type of slag, low hydrogen would be an 8, and we would have 7018, which you know all too well. And then there are more designations in the standard that you cannot possibly memorize. But I do want you to memorize what the KSI are, if it is all position or only flat or horizontal, and some numbers that we use very often, like 6010 and 7018 that we have already mentioned before. So let's see an example. Here we have 6010, 60 KSI, and we can have 118, right? That means 100 KSI tensile strength. I want to draw your attention to this. This 10 that meant cellulosic electrode. Cellulose is an organic that when it burns ends up generating quite a bit of hydrogen. And hydrogen causes cracking in very strong metals. So no surprise, we use a 60 KSI with a 10, that is the cellulosic coating. Now, if I have an 18, that means low hydrogen, then I can go high in strength, because if I have low hydrogen, my risk of hydrogen cracking is lower. And then I would have a 118. Even then, 118 is an electrode that might more often than not require preheat and very special care to prevent cracking. So I mentioned to you that the third digit can be a 1, that means all position, can be a 2, that means flat and horizontal, and also is a 4. That is quite an uncommon number, but I want you to know that means that goes in the flat and horizontal, can do overhead and can do vertical down, but it cannot do vertical up, right? And here we have about the last digit. And you don't need to memorize this other than the 0, that is the 0 that goes with 6010, that is a high cellulose sodium electrode. And I will see later today why I'm putting this emphasis on the sodium. And this electrode typically runs in DC electrode positive. And there are good reasons for that. If it finishes in a 1, for example, 6011 is a high cellulose potassium. And potassium and sodium are these like elements that lose an electron very easily. Potassium loses it more easily. And this can run in AC, electrode positive, or even electrode negative. Here in Alberta, we use 6010 a lot because we can pay for rectifier machines. When I did some welding in Argentina, however little I did, we were using 6011 because we were using transformer machines that run on 6010, or can run on AC. This would be 6011. We can have some rutile sodium electrodes, would be 6012, and many other ones. And here we have the 8 of the 7018, right? It says low hydrogen, potassium, and has iron powder. What matters about the iron powder is something somewhat similar to metal core, right? The fact that we have this metallic, this powdered iron, this powdered metallic alloy, increases the deposition rate. So when you see that electrodes have iron powder, like 7018 has 25% iron powder, 7024 has 50% iron powder, and it's a super high productivity electrode because it's like dropping iron powder all over the place. And here we have some more that is for your notes about electrodes like 6010, all position cellulosic, DC+. When we discuss the arc physics, you're going to see that hydrogen, actually, I'm not going to get into details because it's something that is part of our research now, but everything indicates that hydrogen concentrates the arc quite a bit. When the arc is concentrated, it has a lot of force, a very strong arc, and that gives us high penetration, the possibility of like burning through rust, oil, paint, dirt, pretty much everything, right? This is very used by pipeline welders here. 6011 is pretty much the same thing. Of course, if you weld, you would see some subtleties, but the biggest difference between 6010 and 6011 is that 6011 can run on an AC machine, but 6010 is not graceful on a transformer type machine. 7018, I'm jumping one here. 7018 is limestone coating, iron powder, low hydrogen, and runs typically DC, electrode positive, can also do AC, and is what we typically use for the fill and cap in the pipelines. It's because it's low hydrogen, it's good when we have issues in which too much hardness could cause cracking. Removing this line is a little bit more difficult in 7018 than in 6010. In 6010, it's essentially the slag falls by itself. And it gives us also really good properties, impact properties. And 6010, not so much. And 7024 is also 70 KSI, only flat and horizontal. And the reason is it has so much iron powder that it makes it more than a weld pool makes a swimming pool. And you can make welds very fast with a very fluid slag. But as long as you're in a simple situation, like flat and horizontal. Here you have more of a list of the electrodes available. Again, I care that 6010 and 7018, you understand more or less well because they're so well used. And I just explained, and I would like you to remember that 7024 is an electrode used for what is called high productivity in the world of stick welding because of all these iron powders. And 6011, I want you to keep in mind that because we switched the type of covering from sodium to potassium, now these open up the doors of using AC. All right, I have a question now, and a question I haven't explained yet, but I did explain way back when we were talking about terminology, but let's see how much we can put together now back in time. Why would we use 60-10 to make why is it possible to use 60-10 to make the route in pipelines when those are hydrogen sensitive materials? I know why I want 60-10, because it has high penetration, it can cut through all kind of impurities. So there are many appealing things for 60-10. But 60-10 has hydrogen, and I'm welding a hydrogen sensitive material. How can it be? Why don't we use like a low hydrogen electrode for 60-10? How are we solving the problem of how do we solve the problem of using a hydrogen generating electrode with hydrogen sensitive materials? Ah, ha, 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 ha. All right, yeah, guys, it's not fair. Okay, so here we have two guys who have handled 60-10 and 70-18 a lot. The answer is this: 60-10 generates hydrogen, but if I very quickly, I don't go for a meal and I don't go to sleep. Right after I did my route with 60-10, I follow up with a hot pass with 70-18. And if you remember, the hot pass means a pass in which we deposit a bigger bead. And because it's a bigger bead of 70-18, that one doesn't have problems with hydrogen, will cool down relatively slowly. But most importantly, it's going to be heating up the previous layer of 60-10 and baking off the hydrogen that was in the 60-10. So if we didn't do the hot pass after the 60-10, we could have problems. Now, something funny that we mentioned here in the chat is, some people, and I've seen this in procedures, and it seems to work, they make a hot pass using 60-10. When I confronted the engineers, I said, look, I don't believe that's a good hot pass. They say, no, it's not a hot pass. It's 2 root passes, and the hot pass comes later. I don't really know what to say, but I would like all of you to be aware that it's okay to do something like using 60-10 with high hydrogen in a situation that is hydrogen sensitive, as long as I can follow up quickly with a hot pass that is going to bake off this hydrogen, and then life can move on as usual. Never go back to a 60-10 right after the route. Okay. Flux core wires. Flux core wires have something that is kind of funny. That's why I put it after MIG and after stick. They can look like a MIG wire. You can have an E70T. The T means tubular, and then when we hear the T of E70 or E71T, we know we're talking about flux core. Good. The E means electrode in this case, and we're not going to be using it as a rod, so we're also good. Here's a trick. Now, the number 70 or 71 does not mean 71 KSI. We have to split that number into the 7 of the 71. The 7 alone means 70 KSI. And then the other number, the 0, means 1 means all position, and the 0 means only flat and horizontal. So it's, I don't know who came up with these standards, but they're not super consistent with each other, right? So if I tell you an E70 wire, strength 70 KSI. If I tell you it's E71T wire, strength 70 KSI. Not 71, but 1 is good for, the 70 is good for flat and horizontal only, and the 71 is good for all position. The T means tubular. And then this is followed by this usability designator. This is similar to what we have in stick welding, in which 2 digits gave us the strength, and other 2 digits gave us the type of flux and the usability it's gonna have, right? And in this case, in addition of the type of fluxes and the usability it would have, it also says what type of gas should we use, right? C means that we are using 100% CO2. M means that is a mixture of gas of 20 or 25% CO2, 20 to 25% CO2 with the rest of argon. If we put no M and we put no C, that means self-shielded. And then, of course, like this keeps going, but I wanted you to have a sense of this designation. Electrode 7, that would be the strength. 0, 1 meaning flat and horizontal or all position. T meaning flux core wire. This other digit that talks about the chemistry of the flux and the usability of the flux. And this other one is what type of gas we would have. I put nothing, self-shielded. I put an C means all CO2. I put an M, is a mixture of argon CO2 with about 20-25% of CO2. And here you go, you get to see E70T 1, 2, 3, right? Those are the different type of slag systems we would have, right? And this means self-shielded. This means argon CO2 shielding. And I don't see anyone that is pure carbon shielding here, but here you have the ones with the G. What the letter G, much as before, means a wild card for the manufacturer can do pretty much anything they want. So if you specify any of these outside the G, the electrode should be interchangeable between brands. Although flux core starts getting tricky, but it should. When you specify a G, you're stuck with a vendor because the G of Lincoln is not the same G as Hobart. All right, the fun never ends. Subarc wires and flux. Now things get like a little bit more hairy. Look at this. Subarc has a particularity that no other welding process has, and it is that the filler metal and the slag system come from separate. It's not the case of stick, in which the flux system, the fluxes are stuck to the wire. It's not the case of flux core because the fluxes are inside the wire, right? MIG and TIG don't have fluxes, but in subarc welding, I have a wire and I have a flux. And now things get interesting because, for example, if I want to weld on rusty plate, we all agree by now, we want higher silicon and higher manganese. And do we get it from the wire or from the slag, from the fluxes? But we have to choose, because if we get the manganese from the wire and the manganese from the fluxes, we might end up with like a diamond hard, like a weld that is gonna be cracking, right? And so typically wires and fluxes are sold in some sort of a package. And if we want to mix and match, that's okay, but we have to know what we're doing. So the designation for subarc welding, it starts with the fluxes, then it talks about the wires. So it starts with an F. That means a subarc flux. If it says FS, it means that the fluxes are a mixture that includes crushed slag, which saves money but we have to know what we're doing, because when we crush old slag, it might not be the same one as fresh one. So F or Fs here. Then we have 3 spaces, right? And this is similar to flux core. The number that follows, for example, is 7, means 70 KSI, right? They don't write a 70 anymore. They would write only a 7, and meaning 7 KSI. And then what follows is quite complex. It's just a letter. So if I say FS7, means I'm using a system of fluxes that includes crushed recycled slag. The 7 means I would expect the filler metal under particular conditions to end up giving us 70 KSI. And the A, it means that the tests were done as welded, or if I put here an FS7P, means post-weld heat treated. It got interesting. And then there's something even kind of crazier. It's a number that says, at what test temperature this gives you a minimum of 20 foot-pound in toughness, right? So if here we see a 6, means at minus 60, we have 20 foot-pound. I'm doing all this in the imperial units. That is what they use in the US. Although in Canada, all our standard Canadian standards are in metric. But this is what happens. We can write our standards in metric. When you go to the shop to buy 7018 rod, you say, please give me a 7018 rod. You don't say, give me a 4318 rod. That would be the metric equivalent. So if you have these standards, you'll know very quickly how to do the conversion if you need it. But I'm teaching you the language that most people use here in Canada. It's crazy, right? The Americans have no problems. The Germans have no problems, right? But Canadians are confused. The Canadians sometimes speak like Americans and sometimes like the Germans. Let's say we're bilingual. All right. After the fluxes, then comes the specification for the electrode, and that starts with an E, right? And the E letter is specifies the electrode, and then what follows is the designation of the electrode, right? Which I'm going to show you later. It talks about the chemical composition of the electrode. It's not about the strength anymore. And if the electrode was, for example, a metal core wire, it would be an EC type of, it would be an EC type of designation. It's not really consistent with the other things we have seen, right? And then if we want some more, in addition of specifying the flux, in addition to specifying the metal, the filler, we specify the weld metal. I don't have enough experience writing procedures for subarc welding in which I need to use this. I would like to know more, but this notation sounds so much more difficult than what we have seen with stick welding or MIG welding, right? But this is the way it is. Here you have an example. So this is for a low alloy electrode. And FAA6 ENI3 NI3. What does it say? F. We're talking about, when we see this, we know it's a subarc welding specification. The F, that is only for subarc welding, means the flux. The 8 means that the deposited metal under standard test conditions gives us 80 KSI. The A means those 80 KSI were measured as welded. The 6 means that this weld should meet a toughness of 20 foot-pound at minus 60 F. Yeah, which would be okay for most days in Edmonton, right? F86. Then E means, let's talk about the electrode, Ni3. This Ni3 means what the chemistry is. In this case, it's kind of a 3% nickel electrode, but you shouldn't be fooled thinking that it's always like that easy, right? And then what we have here is the composition of the weld metal. All of these things done under standard conditions. And guess what? It should be Ni3 that is more or less the same as the filler metal. This case is a homogeneous weld, right? Okay. I want to tell you very, very briefly a case study that, that I saw this published online. I have not talked to this guy, but it's something that touches us closely, although not in time, right? This is some time ago when Imperial Oil wanted to see if they could do their projects faster, and they were considering flux core versus stick. Once upon a time, there was a big debate. Today, it's not a debate at all. It's just, if we can, we do flux core, and if we don't, it's because we couldn't, because we don't know or don't have the equipment or some reason. But they were comparing this electrode 8081G, and what is this? Like, sorry, 8018G. So this is like 7018, but even stronger, right? So low hydrogen, all position electrode, right? With some amount of proprietary like pixie dust. So this G means you cannot get the 8018G from a competitor. If this was Lincoln, you couldn't get the Hobart one, because it might not be the same. So this required at this high strength to preheat to 350 Fahrenheit. If you can avoid preheat, you're a much happier guy. But if it cracks, you're very unhappy and you still prefer to preheat then. And it compared it with flux core electrodes, 71T1 and 81T1, right? So in this case, under standard conditions, the 7 means 70 KSI strength, and this 8 means 80 KSI strength. In this case, they were using, although they didn't put it here, they should have, they're using an M designation, right? Because they have a mixture of argon and CO2 shielding gas. Because this type of weld, under the conditions they were doing it, they were obtaining 90 KSI of tensile strength. So the electrode guarantees you a minimum tensile strength under standard conditions, but nobody prevents them from giving you higher strength. In addition, now that we are getting to know some metallurgy, you realize that if you start playing games with a heat input, for example, if I have a lower heat input, I can have a smaller T85, faster cooling rate, and end up with a harder and stronger material of the same alloy, just because I was playing with volts and amps, right? So they were doing this type of game, and they got a very high tensile strength of this material that was specified as 70 KSI and 80 KSI. And because they were using flux core, they could use a narrower bevel. And we know that the cross-section of the bevel tells us how much metal we need to put in. And if it is narrower, we need less metal, and we need fewer passes. And look at this. The bottom line here is that by switching from stick welding to flux core, they had like enormous savings, 40% savings. And in this case, the case was kind of self-evident. But pretty much every time you do some sort of a cost analysis, comparing stick welding with flux core, if you have the equipment, if you have people trained to do flux core, very often, especially if you have some amount of production, flux core is going to win. The advantages of stick welding, that is flexibility, are becoming kind of niche advantages and and liabilities when we talk about production in, especially production in shops. All right. So I think this was it about the naming of welding consumables.